Dear all, welcome to our today recitation session. Today we will solve questions about connectedness, compactedness, their relations with continuous maps, and also uniform convergence. Okay. Problem 1. Yes. Let XD be complete metric space and f from x to y a continuous function if A is a paracompact, precompact, or paracompact subset of X, prove that A is prove that F is uniformly continuous on A. Okay. So X is complete metric space, complete, and A is precompact, then A closure is compact. We know A is paracompact means A closure is paracompact. In complete metric space, closed subset are complete. So that said, A closure is compact. F is continuous on compact set. A closure implies F is uniformly. Any question? Uniformly continuous on A closure, but A is subset of A closure implies F is uniformly continuous on A. Okay? Problem 2. Do you have any question? No. Again, we have a compact metric space, this time compact, not complete. Compact implies completeness, compact metric space. And f function x to x such that d fx fy less than dxy, distance between xy, whenever x is not y. If x is y, it's equality. Okay. What's the question? The question is this. Prove that theta given like this, xr, defined by theta x is dx fx. is continuous. In fact, it's a uniformly continuous function. Hence, prove that by using continuity of theta, prove that there exists unique. This symbol means there exists a unique point x in x such that fx is x. Now, continuity. Okay, given x, y in x and sorry, like this, and x, y, and x with x is not y. X is not y. Observe that theta x minus theta y, which is by definition fx minus dy fy, up. This is less than what? Y. Okay, as x is not y, this is less than 2xy. Also, if x is y, then theta x minus theta y is 0, less than any positive number. After these two observations, choose. Now we will determine delta epsilon over 2. In fact, this function will be uniformly continuous. Then phi x minus phi y again here I need to say okay, then less than 2pxy is 2 times epsilon over 2 is epsilon. Whenever if this is 0, then theta x minus theta y is 0, less than epsilon over 2, implies theta is uniformly continuous function. Our delta does not depend the specific x, specific elements of the metric space X. Uniformly continuous function. Okay, for second part, clearly as fx and not y, so there exists at most one fixed point of f half if x, y is fixed point, was fixed point of f with x not y, then by definition this thing as a fixed point of f we have, but dxy here this property is given if x is not y, dxy, but this is a contradiction. Dxy cannot be strictly less than dxy, implies there exists at most one fixed point of f, i.e. fx is x. Okay, what about the existence? Existence. Assume contrary, that fx is never x for all x in x, i.e. f has no fixed point. Choose fixed, let's say fixed, some x in x, and observe the fx f of x by definition of, property given in the question, is less than x fx, as x is not fx. Define xn as theta fn minus 1 x. The fn minus x fn x. This fn means n times composition, okay? N times composition. Fn means f composition f, n times. Okay. This is a well-defined sequence in real numbers. Clearly implies xn is bounded from below, and by property in the question, xn plus 1 is this theta fnx. This is minus f. We can write like this: f composition fnx, fn plus 1x. This is less than the fn minus x, fnx. This is xn. As theta fn minus 1x. And as a default, define f0 as identity function, i.e. f0x is x, f0, the identity function. Here, n equals to 1, this becomes f0x. Okay. So, also define, well, this implies what? This implies xn is decreasing sequence. seconds in R. Therefore, by monotone convergence theorem, Xm is convergent this sequence in R. Now define another sequence, Yn as n. We know, okay, as X is compact, there exists subsequence of Ykn of Yn with limit Ykn is Y in X. X is compact. Now, here, then by continuity of this theta, xkn is theta, we can write like this, ykn converges to theta y, as ykn converges to y. By definition of sequences xn and yn, we have this equality, okay? This equality. On the other hand, also by continuity, of fr, r is here kn plus 1 minus kn, fr ykn equals to fr y. If f is composition, finitely many f is continuous, then finitely many composition of f is also continuous. But what is this? Here we have, this is ykn plus 1. And limit is unique. Ykn plus 1 converges, it is theta phi. We have what? And theta y is here. Same. Okay, these two are same. Again, one more time. Again, by continuity of theta. One more time. Composition, not composition, image continues to theta fry. Theta y, theta fry. Okay? Here, this is what x kn plus 1 implies theta y equals to theta fry. But this is what d y fy strictly greater than theta, so d or fry r plus 1y. So we have a contradiction. They cannot be equal. Implies, in fact, there exists x, this is unique, such that our f x is x. I mean, x is fixed point of f. Question 10. Okay. One may provide a simpler and nicer solution, but this is my solution. Problem 3. Up to here, do you have any question? No. We have a function from reals to reals. This is a problem 3. We defined by fx is 0 if x is irrational or x is 0, and f x is 1 over n if x equals to m over n with, we may assume this n is positive. This greatest common divisor of m and 1. Sorry. And n is greater than 0. Always we may assume n is greater than 0. Show that our function f is continuous at every rational number number 0 and discontinuous at every non-zero rational number. Every non-zero rational number. Okay. Solution. First, show that for here. First, f is discontinuous on q star. Q. So let xn be sequence of irrationals such that irrationals x m over n, then limit fxn is 0, isn't it? This is not 1 over n. One more step, let me write one more step. Limit 0. At irrationals, our function is 0. I can find such a sequence because irrational numbers are dense in real numbers. So 0, 1 over n, which is f m over n, implies f is not continuous on q star. Q star. What about continuity at 0? F is continuous at x equals to 0. We have here three cases. We will choose first. Let xn be any case, any sequence, such that xn goes to 0. Then we will show that f of x sub n goes to f0 and 0. But how? Here we have a three case. xn is eventually rational. I mean, after some finite number, all terms of the sequence x sub n are rational. Here, one may assume xn is rational, because for convergence, a finite number of points is not important in messenger for all n. Here, this means not right. All but finitely many, and xn is rational. The second case, xn is irrational. There are possibilities. Again, one may assume, without loss of generality, xn is rational for all n. Okay, I will cover these two cases in another case. Assume xn is not eventually rational or irrational. This implies there exist two subsequences and xln of xn such that these are rationals, these are irrationals. And I may arrange the xkn as xln so that arranging these two subsequences here, let me write rational and contains all rational elements of xn similarly, and contains all irrational elements of xn. Either xn is either rational or irrational because it's a sequence in real numbers. Every real number is either rational or irrational. Now, okay, one must show xkn converges to 0 and xln converges to 0, then clearly xn converges to 0. Here, let me write here, covered by this. Okay, so this is a rational sequence. Must show not this, sorry, f, sorry, f0, which is 0, f0, which is 0. Okay? Then one is obvious, isn't it? The limit fxln, as this is a irrational numbers, limit 0, which is 0. What about the other case? Limit fxkn. This is limit mkn over qkn. Sorry, here is a pkn, qkn. And f. Another page. As xkn converges to 0 implies that exists, implies xkn is bounded, so there exists m greater than 0 such that absolute our xkn is pkn, qkn, which is less than or equal than. Claim this qkn is unbounded sequence. Assume contrary, again, contrary that this q sub kn is bounded. This is natural number. Pkn is a integer but not 0. Their greatest common divisors are 1. Qn is bounded. Then we have pkn is less than m times qn, implies as positive pkn is bounded. Therefore there are finitely many possibilities for pkn and qkn. So is finitely many possibilities for xkn. It means xkn is eventually constant sequence. This is a contradiction, implies. But how? Almost. If eventually constant sequence implies limit xkn, which is limit some p over q, implies there is n0 for all n greater than n0. Xkn is p over q, but this is not 0, as p is not 0. But in the beginning, we assume that limit xn is 0, then limit xkn is 0. This is desired contradiction, implies qkn is unbounded sequence. Okay, we have unbounded sequence. Okay, now we are almost finished. Limit xkn equals to limit pkn, qkn, let's say f, which is limit 1 over qkn, unbounded, implies this is 0. As qkn is unbounded. But this is f of 0. Now, third one, continuity on here, irrational numbers. let xn is seconds here. Here, let me call this observation star. Xn is seconds in R. Sorry. Let explain here and xn is seconds with xn is x. I need to show that f of xn converges to f of x. First case, I can assume by our observation, we may assume xn is rational seconds or irrational seconds. First assume xn is irrational seconds. Then limit f of xn is limit 0, which is 0, which is f of x, as x is irrational. Assume xn is rational sequence. Then by star, if xn is p and qn, then qn, same arguments, you may see that qn is unbounded. Therefore, and using same arguments, and using then by star and using same arguments. And qn is unbounded, so limit f xn equals to limit 1 over qn, which is 0, which is f of x, as x in here. Therefore, f is continuous on. Oh, again, is a so long solution. It is possible that one may provide some simpler, shorter, and nice solutions. Continuous on here. Do you have any question? No. Problem 4. Let this function be continuous, where x is compact metric space, where our x is compact metric spaces. Suppose limit f of xn is y for some sequence xn in x and y in y. If f is 1-to-1, if f is 1-to-1, prove limit xn is x and with f of x is y. Okay. Solution. F is continuous and x is compact. As f is continuous and x is compact, f of x is compact subset of y. This implies compactness, implies closedness. Fx is closed with f of x n goes to y implies we have y in this compact set, i.e. y equals to f of x for some x in x. Up to you, do you have any question? So plus f is 1 to 1. So you can write like this. As f is 1 to 1 continues on compact set x, f inverse f of x to x is continuous function. Then, as this is a continuous function, limit xn, which is limit of f inverse fxn, as f inverse is continuous and fxn converges to f inverse y, which is f inverse fx. Okay, this is x, small x, sorry, x. Okay, we are done. Do you have any question? Problem 5. Let fn be a sequence of real valued functions, on a metric space X, that converges uniformly to a continuous function f on x. Uniformly means fn convergence to f in submetric, uniform convergence metric. If limit xn is x, then show that in fact limit fn xn is f of x. Solution. As f is continuous, we have limit f of xn f of x, and xn converges to x. So we have this given epsilon greater than 0, there exists mu n sub 1 in natural numbers such that for all n greater than m1, f of xn minus f of x is less than epsilon over 2, and there exists n2 in n such that for all n greater than n2, d sub fn f less than epsilon over 2. Choose n0 maximum of these two guys, these two natural numbers. Then this fn xn minus f of x. Observe that. Sorry. fn xn minus f of xn plus f of xn minus f of x. This is less than or equal to fn xn minus f of xn plus f xn absolute minus f of x. But this thing less than or equal to d sub fnf, we have less than or equal to d sub fnf plus but this is less than epsilon over 2, which is epsilon for all n greater than 0, implies limit fn xn is f of x. Okay? Do you have any question up to here? Huh? Uniform convergence means convergence in the submetric. Here I am using it. Xn is some elements of x, but supremum taken all x in our metric space x. So we have this inequality. Then the result. Okay, we conclude the result. Okay. Question 6. I mean problem 6. Our sequence Fn given like this are defined by fn x is x to the power n for x in here. Show that fn converges pointwise. I mean, for all x in here, fn x is convergent in real numbers pointwise, and find its limit. Is the question, is the convergence is uniform. The second part answer is no. We will show that. Solution, so xn goes to 0 if x 0, 1. If x is 1, it's clearly 1. Call this f. Then fn goes to f pointwise. What about it's uniform or not? No, second part, answer for second part. Answer is no. How? Let me calculate this distance. Supremum at 1, fn1 is 1, f1 is 1, so at 1 this is 0. We have this equality. In fact, you may take the supremum in here. 1. Fn1 equals to f1 equals to 1. Here, f of x0 equals to supremum x to the n this is 1, but how? Question mark. Let me give some explanation. To function here to here, the real numbers, continuous, connected, and xn 0 equals to 0, xn 1 equals to 1, then by IVT for all x statics. So are in this interval there exists x0 in this closed interval, in fact x0 in 0, 1. Sorry. So such that xn x0 is r. So we prove question mark. Proved question mark. So as the sup fn f is 1, fn f uniform. Do you have any question? Problem 7. Up to here, do you have any question? Let we have this function r be a continuous function such that g of 1 is 0. Show that the sequence fn of x g of x for x in here converges uniform with a constant zero function to constant zero function. So, okay, here for solution, one must shove this soup. Is it FM? Yeah, FM. 0 as n goes to infinity. Let's define h1 of x, so which is g of x, and supremum, which is hn, is in here. Not that as x to power n as roll x 0, 1. We have hn plus 1 x is less than or equal to hn x for all n and for all x in here. For all n. It's in here. In fact, in particular, hn x is less than h1x, called h1 is h. After this observation implies alpha n is decreasing sequence, clearly, and but 0 of n for all n implies by monotone convergence theorem alpha n converges to alpha. I'll claim this alpha is 0 in R. Claim this alpha is 0. Then we will finish the proof. Alpha is 0. Again, assume contrary. Alpha is greater than 0. Now, as g is continuous function and g1 is 0 for epsilon equals to alpha over 2, there exists delta greater than 0 such that if the x1 less than delta, we have f of x şöyle equal star g of x minus g of 1, which is g of x less than delta here. Not delta, epsilon equals to alpha over 2. But here, this set can be written like 1 minus delta 1 as a subset of 0-1 closed interval. Then on this set, I'm choosing delta sufficiently small that 1 minus delta is greater than 0. G of x is less than alpha over 2. This is less than alpha, but by star, this is less than alpha. So from here, we conclude alpha n equals to this set is given supremum h n x, which is what? X in here. Instead of this interval, I can choose the smaller one as above observation, smaller one, g of x. In fact, 1 minus delta here. As g is continuous on 0-1 compact, there exist real numbers such that g of x is less than n on this set. So this in fact, after the last observation, we have n times supremum xn. But this is n times. This goes to 0 as n goes to infinity, which is a desired contradiction. Oh, sorry, let me write here. This is a contradiction. Therefore, our alpha is 0. So our alpha 0 implies B sup implies what? What's the name of function? F of n 0 uniformly on 0-1. Do you have any question? Problem 8. Prove that this set one less than x squared plus y squared and is less than 4 is compact and connected. Compactness. Compactness is easy. Define F. Call this set as A. F is continuous. Plus and A equals to F inverse 1, 2 as a radius. Yeah, 4. Closed. As closed as F is continuous. What about the boundedness? Clearly, A is the subset of this both implies A is bounded. Therefore, by Heine-Borel theorem, A is compact. What about the connectedness? So we will show that our set A is PET connected, therefore is connected, okay? We will show that A is in fact arcwise connected or PET connected. We will find for any 2 points, we will find a path which combine the 2 points connected. Let X, Y in here, A. Then define a map. Then clearly X is and Y can be written in polar coordinate like this. Some R1, R2. Clearly, and less than 2. And define a map. F 0, 1, 2. Now the R square, but then we will show that image of this F. Define it half. Take the Z. Oh, sorry. Here, T, 1 minus T, R1 plus T, R2, E2, 1 minus T, theta 1, şurada bir i'miz var. I, plus T, theta 2. We will show that for all T and 0, 1, show 1 minus T, R1, T, R2, in fact, Y. So if you call this is Z, the modulus of z equals to this is modulus of z. If I call this z, modulus of z. But how? Without loss of generality, assume R1 less than or equal to R2. Then 1 less than or equal to R1. This is 1 minus T R1 plus T R1. Okay? As for all T in 0, 1. This is less than or equal to as R1 less than R2. One minus T R1. I change this component R2. All things here positive, we have this inequality. Again, R1 is less than or equal to R2 implies R2 T times R2, which is R2 2. We are done. I.e., we conclude modulus of Ft is implies modulus of T here, i.e., F, this closed set belongs to A. With f of 0 is x and f of 1 is y. Clearly f is continuous. Implies A is arcwise path connected. Implies, in fact, it is connected. Sorry. Connected. Do you have any question? Problem 9. Let IM be sequence of non-negative real numbers is given for all n, and limit an is 0. Consider the following set of sequences. The following set of sequences. Nasıl bir set? A is kısa n, the absolute of kısa n less than an for all n. Now, prove that A is closed subset of Bn. Bounded sequence in natural numbers. Bn. We have some functions. Theta e, Bn then from Bn to R e be defined by psi e, theta sub e psi is psi 1, psi e, where psi is this sequence in A. Prove that theta e, theta sub I is continuous. Also prove that theta I is precompact. Subsets of hence prove that A is compact subset of En. Solution. The first, A is closed. How? Show that A is complete. Show that A is complete. Given, let psi n be Cauchy sequence in A. Implies this psi m is Cauchy sequence in here, but this set, this metric space is complete. We have psi n converged to psi here. Claim this psi in fact belongs to our set A. I.e. psi n and absolute less than n for all n. Given epsilon greater than 0, there exists m0 in n such that d sub psi m psi less than epsilon for all m greater than or equal to m0. Then, for all n, psi n equals to psi n minus psi n m0 plus psi n m0. This is less than or equal to psi n up to m0 and psi n m0. This is less than epsilon plus an for all n. As a result, we have, psi n less than epsilon plus an for all epsilon greater than 0 for all n in n. Then by epsilon lemma, we pass the new page. Then by epsilon lemma, in fact, psi, yes, psi n less than or equal to an for all n implies psi n here implies A is complete, implies A is closed. Okay, what about the second part? Second. Theta sub I is continuous for all I. Let psi m be. I will use here sequential continuity. Is sequence in A with psi. Okay. One must show theta I psi m converges to theta I psi. Given epsilon greater than 0, there exists m0 in natural numbers such that d sub psi m psi is less than epsilon clearly psi m I minus psi I d sub, call this J. Isn't it? For all j equals to 1 to I implies, in fact, rho is theta I psi m, which is psi m1, psi m2, psi I m, distance to psi 1, psi I, which is theta I psi, less than epsilon for all m greater than m0 implies theta I psi m converges to theta I psi. Hence, theta I for all I is continuous. This function theta is continuous for all I. Third, this set is precompact. Subset of this set. Here, boundlessness implies and only if precompact in RE. I will show that this set is bounded in this Cartesian product. Okay. For all theta I psi in psi EI, V implies psi in A implies psi 1 j less than ij for all 1 to I. Let R be this number I plus 1, then rho infinity origin one to I. So this is clearly less than or equal to R. Only implies our set I is subset of this ball, implies phi I A is bounded, and which implies that this set is precompact. Precompact set. We come to the last part. Last part, fourth. What is it? A is compact, subset of Bn. Only show that this A is precompact, and in the first part we have shown that A is complete, so we will conclude that A is compact. But how? Given epsilon greater than 0, there exists E in here such that for all n greater than E plus 1, epsilon over 4. As theta A I is precompact, there exists X finitely many xk let's say we may, for this epsilon, we may choose the finite many say okay x1, x2, xk in here. Such that theta I subset of K epsilon over 2 J. In fact, we may choose xj in here, there, A and block assume K equals to I. It's not so important. Therefore, there exists psi j in A such that J. Then, in fact, we have, therefore, we have this set, the subset of I, both two. No, we don't need to assume this is k equals to a, okay. We don't need such an assumption, okay. Okay, from here, claim, what is our claim? Claim is this. In fact, this A subset of j equals to 1 to k, here the soup metric, kısa j, epsilon, okay. Let kısa be A, then theta e kısa is belongs to this pole. Theta I kısa j epsilon over 2 for some j. Therefore, kısa 1 minus kısa kısa n epsilon over 2 for all n equals to 1 to I. So from above, this implies what? Implies j less than epsilon over 2 plus epsilon over 2 epsilon. Tamam. But if m equals to I plus 1, we have kısa n j minus kısa n no, here you don't need to write like this. Sorry. Clearly epsilon over 2. We have chosen here. Now we will use the argument psi j minus psi n less than plus, but this is less than an plus an, so less than epsilon over 4 epsilon over 2 implies for all n, epsilon ni minus epsilon n less than epsilon over 2 implies super, let me write, d sup psi I psi as a j less than or equal to epsilon over 2, which is less than epsilon. Therefore, A is precompact, but also complete. Implies A is compact. Up to here, do you have any question? It's a little bit long. 22. Now, question 10. We come to problem 10. If you don't have a question, I will continue with problem 10. But what it is? Let xn be a sequence of real numbers. Okay, this is the last question which I will solve. If this limit xn is what? Then prove that pi over 6. Solution. We will use homeomorphism theorem. So we need to construct a one-to-one continuous map on compact set. Define f. F is two real numbers as f of x is 2x plus sine x. This is compact, clearly. This is continuous, and f pi over 6 is pi over 3 plus 1 over 2. Claim f is 1-to-1. Given xy in 0 pi with x is not y. Block without loss of generality assume x is less than y. Okay, f is continuous on clearly this set and differentiable on where xy. Then by mean value theorem there exists alpha in here, this open interval, such that f of x minus f of y, x minus y is f prime alpha, which is 2 plus cosine alpha. 2 plus cosine alpha. As cosine alpha is here, we have implies f of x is not f of y, implies F is 1 to 1. Therefore, by homeomorphism theorem, F inverse F here too. Sorry. This is a pi. Yes. Zero pi with continuous function. Then fxn equals to 2xn plus sine xn. Call this x. Sorry. Call this x and this f of x. Still goes in f of x. It limit f of x n equals to pi over 3 plus 1 over 2, which is f pi over 6. We have limit xn equals to limit f inverse f of xn, which is limit f inverse f, sorry, we have no limit here, pi over 6 is pi over 6. We are done. As f inverse is continuous. Okay, this is end of today's recitation. Do you have any question? Now I am stopping the recording.